Hi everybody, I hope that all of you are doing well. So today we will do lab number 8, and lab number 8 is about the RLC circuit. So what is the RLC circuit? The RLC circuit consists of the following, as you can see: function generator right here, resistance right here, coil right here. It should have around 100 or 200 millihenry, and capacitor here 22 microfarad. So this is the RLC circuit that we will use, and they will indicate the resistance, the inductor or the coil, and the capacitor. So resistance, inductor or coil, and capacitor. So now we can see all of the equipment that we need for today's experiment. We need this coil right here. It can work as inductor. We have capacitor right here. We have resistance. This resistance is 1 mega ohm. We need the oscilloscope, of course, and we need the function generator. And the function generator needs to be set on around 11 kilohertz. I will try to zoom in so you can see the function generator. The function generator is around 11, so it is 11.2 kilohertz. That's great. I will zoom out now and try to connect the circuit that we will use. Of course, we will use these coax cables. They will help us to measure the voltage across the resistance and across the function generator. So now let's connect the circuit, and to do that we start from the capacitor. So the capacitor right here, as you can see, right here, and from the capacitor we go to the inductor or the coil. So it's right here. You can see that we have a coil right here, we have capacitor right here, and from the inductor we go to the resistance, which is 1 mega ohm, and then close the circuit, as you can see right here. So this is the RLC circuit, as you can see. Now what I will do, I will try to connect one of the coax cables to the oscilloscope, as you can see right here, and then connect those terminals across the power supply, as you can see. So I will do that right now. As you can see, we can see the voltage here from the power supply. It is not stable, but we can have it stable, as you can see right here on the oscilloscope. Yeah, as you can see here, so you can see that we have around 1 square, 2, 3, 4 4 times 2, that it is 4 point something, so 1, 2, 3, 4.4 times 2, so that will give me like around 8.2, so we don't need that. I will try to reduce the voltage a little bit down, so let's go here and try to reduce the voltage. So we just need around 4 volt, so 4 volt is enough. Yeah. So let's now double check. Let's see, we have 1 square, 2, 3, 1, 2, 3. I think we still need to increase the power supply voltage. To have around 4 volt. Let's see now. So we have, so we have 1 square, 2, 3, 4. 4 times 1, so that will give me 4 volt. So this is what we are looking for. So that's great. Now I will try to fix the other coax cable right here. So now we know that the function generator is providing this circuit, the RLC circuit, with 11 kilohertz and V peak to peak 4 volt. So that's great. I will zoom out, and then I will try to connect this across the resistance right here. So I will do that and see what we will get. Okay, so let's now adjust the voltage right here and see what do we have. Yeah, so this is what do we have. I will try to adjust this to be right here. So this is across the resistance, so the yellow one. I will try to zoom in. Yeah, so the yellow one right here represents the output signal across the resistance. So now I will try to have both of the signals on top of each other like this. So the yellow one represents the signal or the output across the resistance, this resistance right here, this resistance right here, so across the resistance. And the blue one, or the blue signal, it is it represents the signal across the power supply. So now we have this nice behavior. So what I will do right now, I will adjust the camera a little bit better so you can see this behavior quite clear. Okay, so hopefully that's clear. You can see the damping here. You can see the damping. What do I mean by damping? You can see something like this, that this signal has this kind of damping. And actually, when we have resistance and inductor and capacitor connected in series, we will have this kind of damping. If you go to one of the week 6 sessions, I believe session number 3, week 6, or session number 2, week 6, you will notice that we talked about the RLC circuit, and also we talked about the damping. So you can see that this kind of damping indicates that the amplitude of this oscillation goes down with increasing time. So that's interesting. Now what we are going to do from this data, the thing that we can do here, we need to count like how many oscillations do we have. So I will go here, and then try to count the oscillations. So I will increase the time division, so that can help me to count, and then I will bring this down, so that can help me to count the number of oscillations. So the number of oscillations here is around 0. So we need to count from left to right. We need to count from left to right. So let's see how many oscillations do we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 17, 18, 19, and then 20. So we have around 20 oscillations. We have around 20 oscillations. How to count the oscillations? We need to focus on one of these. For example, I will pick one of them. Yeah, maybe this one. So you can see that when you go up and then return down, so that is one oscillation. Go up and then go down. Second oscillation, go up and then go down. This is the third oscillation. Yeah, so something like this. So now we counted the oscillations. So we have 20 oscillations. 20 oscillations, so that's great. And now we need to measure the periodic time for the oscillation. So how to do that? I will remove the power supply signal, so we don't need it, and then I will focus on this, so you know that we have more than one, as you can see right here. So we have more than one. Yeah, and then go down, oscillating, go up, oscillating, go down, oscillating, go up, oscillating, and etc. Something like this. Yeah, so what I will do now, I will focus on one of these oscillations and try to figure out the periodic time for these oscillations. How to do that? I will go down like this and then try to expand the time scale, so that can help me to figure out the oscillations. So the periodic time is the same between each one of these peaks. If you go like this, you will figure out that it is the same between each one of these peaks. So what I will do, I will just pick the first two and then try to measure the time. So to measure the time, we need to see like how many squares do we have. I will adjust it a little bit like this, so that's great. So you can see that we have 1 square, 2 squares, 0.1, 1, 2.1, 1, 2.1. So we have 2 squares 2 squares 0.1, and we need to time those 2 squares 0.1 by 1 microsecond. By 1 microsecond, so we have 2 squares 0.1 times 1 microsecond. So this is the periodic time. And to get the frequency, you need just to get the reciprocal of the periodic time. So the frequency is equal to 1 divided by 1 divided by periodic time. I will try to show you that from here. So frequency is equal to 1 divided by periodic time. So this is the frequency. I will zoom out to help you see this equation. So the frequency is equal to 1 divided by periodic time. So the reciprocal of the periodic time can give you the frequency for this oscillation. But what you can see here, you can see that this oscillation is damping. Actually, it is going to 0 while it is propagating with respect to time. So you can see that this oscillation, or the oscillation amplitude, will get to 0. And it is similar to the classical mechanics damping system. So I explained that maybe in session number 2 or session number 3 from week 6. So go there to figure out these, to try to watch those sessions so you understand what I'm talking about here. Okay, so I will return everything back as it is. Okay, everything back as it is, and then return back the power supply voltage. So you can see that we have correct output from this circuit, and actually this output, the yellow one, was across the resistance. Now we know the frequency, which is great. We know the number of the oscillations, also that's great. Now we will try to figure out the resistance of the critical damping. So what is the resistance of the critical damping? The resistance of the critical damping, so that happens when these oscillations disappear. So when those oscillations disappear, that will give me the critical resistance or the resistance of the critical damping. How can we do that? We need to change the resistance that we have in the circuit. So what I will do now, I will zoom out, as you can see right here, and try to adjust the camera so you can see what I'm talking about. So this resistance that you see right here is 1 mega, and actually we don't have a decayed box. We don't have a decayed box, and since we don't have decayed box, I tested like more than one resistance to figure out the resistance of the critical damping. And what I got something like this. So I will show you that step by step, and you will see how this will go down. Like those oscillations will disappear. So the resistors that we have, so we have here we have 10 kilo ohm, and then we have 5.6 kilo ohm, and then 1.1 kilo ohm, and then 580 ohms. So what I will do now, I will try to replace this resistance that we have, which is 1 mega. So now I will remove the 1 mega that we have in the circuit. So I will remove it, and then have 10 kilo ohm. So let's see, 10 kilo ohm. So let's see what will happen with 10 kilo ohm. What is the difference? Connect the terminals again, and you can see now that these oscillations with 10 kilo ohm became smaller. So you can see it became like a few number of oscillations. So you can see that we have 1, 2, 3, 4, 5. I will zoom in and show you that. I will zoom in and show you that. So you can see that the number of oscillations now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 maybe. And these oscillations, or the number of the oscillations, is a small number. You still remember that we got 21 or 20 oscillations. So we got like around 20 oscillations, but right now we have 10. Why is that? Because we changed the resistance. The old resistance was 1 mega, but the new one that we have here is 10 kilo ohm. Now I will change the 10 kilo ohm. So I will remove the 10 kilo ohm from the circuit, as you can see right here. So I will remove the 10 kilo ohm and use 5.6 now. I will use 5.6 kilo ohm. Let's see what do we have with this resistance. Now I will try to read the signal. So also here you can see that the number of oscillations became fewer. Look at, so 1, 2, 3, 4, 5, 6 instead of 10. Yeah, they are around to be disappeared. Just I will show you that step by step. And now I will replace the 5.6 ohm resistance. I will replace it with one, I'll try to show you that, with 1.1 kilo ohm. So let's do that. So with 1.1 kilo ohm, let's see now what we will get. Okay, so you can see now that we have maybe around 2 oscillations. If you focus here, you can see that we have like around 2 oscillations, like 1, maybe 1, 2, 1, 2. So now I will continue with the next resistance, and the next resistance here is 580. So let's now remove the 1.1 kilo ohm and then use the next resistance, which is 580. So this is the 580 ohms. So let's see what do we have with the 580 ohms. So I will connect here, and now you can see that the oscillations disappear. We don't have any oscillations anymore. And this resistance that we applied, which is the 500, let's see, which is the 580 ohms, It is called the resistance of the critical damping. This is the resistance of the critical damping. So if you were asked in the worksheet to write down the resistance of the critical damping, so you need to write the 580 ohms. So this is the resistance of the critical damping. Now I will zoom out again, and try to have the same resistance, which is the 1 mega. So I will have the 1 mega again. So where is the 1 mega? This is the 1 mega ohm. So I will have it again. Remove the 580. So I didn't prefer to test those resistors with you because I tested more than one resistance, like maybe 30 or 40 resistors. So that will take a long time to be done. So what I did, I tested all of them and then picked a few resistors to show you this behavior. Okay, yeah, since we don't have decay box. Now what I will do, I will go back to the 1 mega again. So this is the 1 mega. We have 1 mega ohm. Now I will connect the circuit, as you can see. So we have this behavior again. So I will show you this again on the oscilloscope. So we have this behavior again, this nice oscillation here. Which is this one, this nice oscillation. Okay, so that's great. The next thing that I will do, I will move now. As you can see, I will remove the yellow signal, which is across the resistance, so I will remove it. So as you can see, we are using square wave from the power supply. But the next step in this lab requires us to adjust the input signal to be sine wave instead of cosine wave. Instead of square wave. So what I will do now, I will go to the function generator right here and try to adjust it to be sine wave instead of square wave. Keep everything as it is, keep the frequency as it is, don't change anything, just change the waveform from square wave to sine wave. And then let's go to the oscilloscope so you can see that we have sine wave. This is the input. This is the input signal. Let's see the output now. So the output also is sine wave. So now what do I need to do now? I need to change the frequency and at the same time, so let's have them on top of each other. Exactly on top of each other. So now you can see that the blue one is on top of the yellow one, and the yellow one, yep, matches the blue one. So that's great. Now what do we need to do? Now we need to change the frequency and see what will happen to the output. So the yellow one is the output and the blue one is input, the input signal. The input signal is from the function generator. The yellow one, the output, is across the resistance. So what I will do now, I will change the frequency and then I will record the V peak to peak voltage from the output signal. So let's do that. So what I will do now, I will decrease the voltage decrease it. Yeah, decrease the voltage, and then start to increase it. So now I will have the blue one. So we need the blue one here to see if there is any increase happens to the yellow signal. So I will increase the frequency. While I'm increasing the frequency, I need to change the time scale so we can have this nice sine wave. Okay. Continue to increase the frequency and see what will happen. Yeah, you can see that the yellow one started to increase here, but it will continue to increase the frequency. So you can notice that the sign, the yellow signal here started to increase. So it has like V peak to peak voltage greater than. So let's go back. I'll write that down. So I will go back. Start when they are on top of each other. So here what do we have? Here we have peak to peak. Let's see. So the peak to peak voltage the peak to peak voltage here, we have 1 square, 2 squares. Maybe you would like me to zoom in. Yeah, so I have 1 square, 2 squares times 2 volt. So that means we have some voltage. So we need to make a table, and this table can have voltage right here. So where is that? Yeah, voltage here and frequency here. And then you can write the data that you have. So from the function generator, I have 93.9 kilohertz from the function generator. The voltage here is 2 times 2 squares, so that will give me 4 volt. Great. So now I will increase the frequency and see what do we have. So now I will move to the yellow one. So now you can see that the yellow one has a little bit higher voltage. So instead of 2 volt, so it is 2.2. So we have 2 squares, 0.2. 2.2 times 2, that will give me 4.4 volt. And that's corresponding to 214 kilohertz. 214 kilohertz. See that? So that's correct. Now I will jump to different scale. So I will go to the 0 again, and then jump to different scale from the function generator. So I will show you that, what I'm doing here. Yeah, I try to jump from this scale to the next scale right here. And I will move to see here. We mentioned that we tested 214, so this is 214. I will adjust it to 214. 14. So now I will go back to the function generator, sorry, to the oscilloscope, and try to adjust this. Yeah, so we have 2.2, that's great. Now I will continue increasing the frequency. So what I will do now, I will go to maybe 300 and see what will happen. So with the 300 hertz, so 300 hertz from the function generator, you can see here that we have now we have 2 squares point 6, 2 squares point 6, so 2.6 times 2, so that will give me 3.2, so I believe that's correct. So 2.6 times 2, that will give me 3.2. Let's see here. So 2.6, so no, I'm sorry, so 2.6, so that will give me 5.2, so 2 times 2 is 4, and 2 times 0.6, so that's 1.2, so we'll have 5.2, so 5.2 volt, so that's great. Now I will move to 400. 400 kilo, of course. So with around 400 frequency, you can see that we have voltage from the output signal. We have 1, 2, 3 squares. Oh, 1, 2, 3. 3 squares point, 3 squares point 8. So 3.8 times 2. So that will give me 7.6 volt. So we have 7.6 volt. So 3 times 2 is 6, and 8 times 2 is 16, so we have the 7.6 volt, and that was with 400 hertz. I will continue now to 500 hertz and see what will happen. Yeah, you can see that the voltage across the resistance increased, so I will go to the 5. Let's see, where's the max? Max is somewhere right here. Okay, so this is the max. So the max is around 8. So we have 1, 2, 3, 4, 5, 5, 6, 7, 8. We have 8 squares. So 8 times 2 will give me 16 volt. And the frequency is 463.7. And if you go to session 2 or 3 from week 6, you will notice that I provided you with the plot. This plot represents the output across the resistance versus the frequency, and I noticed that this behavior will be like this, like Gaussian, and the peak of this Gaussian shape represents the resonance frequency. So this is the resonance frequency, which is corresponding to the highest voltage here, output voltage, of course, peak to peak voltage. So now I will continue to increase and go to 500. maybe we can do like maybe we can do like 490, so 490 hertz, sorry, kilohertz. So 490 kilohertz is corresponding to 1, 2, 3, 4. 4 times 2 is 8 volt. And then go to 500. And with the 500, you can see that. So with 500 kilohertz, we have again 2.2, sorry, 2 squares times 2, so that will give me 4 volt. And then when we continue to increase the frequency, you can see that the output signal became very, very small. So this is everything for today's lab, and hopefully we did nice work here, and I could manage to show you some work that is related to the RLC circuit. So I will try to post this video today sometime, so you can start watching this video.